Inverse functions, algebra 2, trigonometry regions. If 5, negative 2 is in the function f of x, then which of the following points will be in the inverse function f? So a couple of things here. First of all, this symbol right here, this little negative 1, f of up to the negative 1, this is not an exponent. So when you see a function name, because f isn't a variable here, it's a function. X is a variable, but f is a function name. When you see that raised to the negative 1, it is not an exponent. It stands instead for the word inverse. It is the inverse symbol. So the inverse symbol is f to the negative 1. And first of all, what does the word inverse mean? Inverse to us means, some people, when I ask class, what does the word inverse mean? People usually say opposite. And that's pretty good. But what I really want you to think of when you think of the word inverse, anytime you see the word inverse, you need to think switch x and y. So inverse means switch x and y. So then this is actually a very simple question, right? Here's 5, negative 2. The inverse would be negative 2, 5. Just switch x and y. That's it. It's that simple. We're going to see inverse graphs and inverse equations, but inverse at the coordinate level is very simple. Just switch x and y. So let's take a look at an inverse graph. Number 2. The graph represents f of x. So here's f of x, and they want to know what would the inverse of the graph look like. What would the inverse? Switch x and y. And if you remember back in geometry, when you did your transformation chapter, where you did your, reflecting the y-axis, rotating 90 degrees, translating by some vector, 3, negative 2, so on, so on, so on. There was one reflection that caused us to switch x and y. And it wasn't a reflection over the axes. It was a reflection over a diagonal line. Well, I call it a diagonal line. I don't even know if that's really the proper word, but a line like this. This is the line, or this is the linear equation y equals x. And so, like, back to this problem here, in geometry, if you had the question reflect across the line y equals x, the coordinates 5, negative 2, the answer was negative 2, 5. And this is your inverse function. And if you had a good geometry teacher, maybe they mentioned that to you while you were doing it. That when you reflect over the line y equals x, you switch x and y, and that's called the inverse. And so the inverse is reflecting across this line. So visually, you can do graphs pretty easily just by kind of picturing what would it look like if I flipped it across this line. And you see the answer here is C. Like it would look something like that, right? The mirror image. And so that's how you could do it. The other option is to think about flipping all your x and y's. Like you do have a couple of coordinates here. Like this is the point 0, 2. Well, that's inverse would be 2, 0. And this is the point negative 2, 0. Its inverse would be 0, negative 2. And then, let's say this is, just to make it easy, negative 1, 1. It's probably not exactly like that, but, well, then we'd want 1, negative 1, which would be, the inverse of that. And so you can visually think about reflecting the line y equals x, but you could also switch any x and y coordinates you have and kind of plot the new graph, as you go. And so that's why the answer here is definitely C. Now at the equation level, I have a function, f of x equals x squared minus 6, and I want the inverse of f. Inverse means switch x and y. But I don't have any y's here. Well, if you remember that f of x is the same thing as y equals x squared minus 6. So if I want the inverse of the function y equals x squared minus 6, what am I going to do? I'm going to switch x and y. So you would make it x equals y squared minus 6. And then I need to change it back to an f of x function, which means I need to solve for y. So you need to switch x and y, then solve for y. Because all of our equations are in terms of y when we do f of x and stuff like that. So now I need to take this expression with this is the inverse, but I need to get y alone. And it's okay if I get it alone on the right, because the left equals the right, I could always switch it. So I need to basically move things away from this. And so how's that process going to work is I'm first going to get rid of this 6. So I'm going to add it to the other side, add 6 to both sides. That's going to give me x plus 6 equals y squared. But I don't want y squared, I want just y. How can I get rid of a squared? Well, I could do the square root. And if I do the square root of both sides, I get the square root of x plus 6 equals y. And this is my proper notation for my inverse function. However, I'm going to write it in my inverse notation, which is my f to the negative 1 of x equals square root of x plus 6. So once you get that y alone, just replace it back into your inverse notation, but don't forget to put your inverse symbol attached to your f. And so that's really it. It's not too bad. At the coordinate level, you're just switching x and y. At the graph level, you're reflecting y equals x and switching x and y, which is what reflecting y equals x does. And at the equation level, which is probably the most challenging, is you're going to change it to a y equals function, switch x and y, and then get the y alone, solve for the y, and put it back in there. Now, there's one kind of cool thing you could do here, is you can confirm it's an inverse function. This problem didn't tell us to do this, but I'll probably ask you to do this at some point, so now's a good time to do it. That if I have f of x equals x squared minus 6, and I now have f inverse of x is a different function, the square root of x plus 6, I can confirm these are inverses of each other if I show that f of f inverse of x equals x. Basically what that means is if I plug one of these into the other, and it doesn't matter if I go f into inverse or inverse into f, in fact it has to work both ways, but I'll just do one here to show you what I'm talking about, that if I plug one of these into the other, I should end up with just x. And so if I were to plug f inverse, which is this whole expression, into f, into the input spot for f, which means, replace my x with what I'm plugging in, I would end up with the square root of x plus 6, that's my input squared minus 6, and the square root squared gets rid of the radical. I just have x plus 6 minus 6, which simply equals x. And if I were to do it the other way, and really you should do it both ways, f inverse of f of x, that would be plugging this whole expression, x squared minus 6, into the input here. So it's that plus 6 in the square root. Well, I can simplify in here. The plus 6 minus 6 cancels out to just be x squared, and the square root of x squared is x. And so this does confirm that it is indeed the inverse of each other. And so, solve for y, switch x and y and solve, but then you can confirm, and I'll ask you to do this at some point, confirm they are inverses by showing that plugged into each other both ways gives you x each time. All right, see ya.